Hello friends, let's continue the remaining part of the pericyclic reaction that is in your syllabus. Pericyclic reactions. In some last lecture we saw some definition of pericyclic reactions. There are types: pericyclic reaction, electrocyclic reaction, cycloaddition reaction, sigma-tropic rearrangement, and the ENE reaction, or we say group transfer reaction. So these are the reactions that we have studied, and only some part is remaining that we are going to continue in this lecture. So here first we have to see the 1,3 dipolar addition. It is most pronounced reaction, 1,3 dipolar addition. So 1,3 dipolar addition is one of the pronounced reactions that we have to study. So generally it is represented in this way: A, B and C contain negative charge, A contain positive charge, and B is the species which contain a lone pair of electrons, and another is the alkane or any other unsaturated species. So other unsaturated species. So this species, especially when we consider Diels-Alder reaction. In Diels-Alder reaction, there are two species such as this one and another species. This is we call diene, and this is dienophile. So diene and dienophile. These are two species in the case of Diels-Alder reaction. This reaction is somewhat similar to the Diels-Alder reaction, where this species is called as 1,3 dipolar species. So this is 1,3 dipolar species, and this species is called as dipolarophile. Dipolarophile. So 1,3 dipolar species and this is dipolarophile. So these are two species. These are the two species which leads to reaction. Reaction occurs generally in this manner. So A, B, C, X, Y. So this cyclic compound we obtain. So this is the product of the 1,3 dipolar addition. And two species are there: 1,3 dipolar species and another is dipolarophile. 1,3 dipolar species and another is dipolarophile. So let's see here which species acts as a dipolarophile, or which species acts as a 1,3 dipolar species. So especially 1,3 dipolar species are the species which contain 3 atoms. So A, B and C. This is 1,3 dipolar species. Now in this 1,3 dipolar species, A is the species which contains 6 electrons in outermost orbit. 6 electrons in outermost orbit. So it may be carbon, it may be oxygen, or it may be nitrogen. All they may contain 6 electrons in their outermost orbit. So they have all ability to acquire positive charge. So here carbon, oxygen and nitrogen are there, which acts as A. So here B is the species which contain 8 electrons in outermost orbit, and another additional benefit is that outermost orbit plus it contains at least one lone pair of electron, maybe more than one, but at least one lone pair of electron. This species is a B. So carbon doesn't have any lone pair of electron, but oxygen and nitrogen, these are two possibilities of being as a B. And C is the 8 electron in its outermost orbit. That means octet completed outermost orbit plus additional one negative charge. Negative charge. Now this capacity is for carbon, also for oxygen, also for nitrogen. All they acquire negative charge also. So these are the species. This is the 1,3 dipolar species. A having positive charge, that means 6 electrons in its outermost orbit. B, octet completed for last orbit, outermost orbit, and also additional one lone pair, at least one lone pair of electron. Here C contains 8 electrons in its outermost orbit. That means octet completed for this octet plus additional negative charge is there. So this is 1,3 dipole species. Let's see some examples of the 1,3 dipole species. There are certain examples which shows such type of compound in reality. So azoxy compounds are there. Azoxy compounds are there. So there are the examples which we call azoxy compound. So these are the azoxy compound NO. As per our norms, it contains positive charge. This contains lone pair of electron and it contains negative charge. So this is 1,3 dipole species. Another example is nitroso oxides. Second example is nitroso oxides. So nitroso oxides are the compound which contain N oxygen and oxygen. Okay. So this contains positive charge. This contains lone pair of electron, more than one lone pair of electron, and this oxygen contains negative charge. So this is 1,3 dipole species. Again another example, nitrous oxides. Nitrous oxides are the another example. Nitrous oxides, another example where N double bond N O. So O negative charge, it contains lone pair of electron and this contains positive charge. Nitrous oxides. Another, ozone is one of the famous example. Ozone, O, where this oxygen contains positive charge, contains lone pair of electron and negative charge. So many examples are there which showing the 1,3 dipole species. Now how this 1,3 dipole species acts? Let's see an example here. How it interacts with another species. That is dipolarophile. Dipolarophile may be alkene. Another species dipolarophile may be alkene, alkynes, imines, carbonyl compounds. So these are the dipolarophiles which react in these reactions. So see example here, we are taking C plus ozone. Ozone is the reacting molecule here. See this negative charge, lone here, and this is positive charge. So when this negative charge attacks here, it attacks on this electron deficient atom. So electron deficient atom is there, and electron deficient atom now it interact and form C. So O, this oxygen, and this oxygen. So this type of structure we call molozonide. We know that molozonide it rearranges into ozonide. Molozonide it rearranges into ozonide, and how breaking of ozonide is there, how the carbon compound form. So that is not the part of our reaction. Our part of reaction is the formation of molozonide from this 1,3 dipole species. So ozone react with this dipolarophile to form molozonide. So this is the 1,3 dipole species, and these are the reactions of 1,3 dipole species. Now one important part remaining from the pericyclic reaction is the drawing of the molecular orbital of the odd carbon species. Drawing of molecular orbital of odd carbon species. So before that we saw the molecular orbital drawing for 4 pi electron system, 4 pi plus 2 electron system, 4 plus 2 pi electron system. So these are the systems where we saw the carbon atom involved which are even in number. But when they are odd in number, then we have to see how to draw the orbital. So let's take an example, which are the odd carbon atom or which are the odd carbon system we have to consider here. So odd carbon system, first and simple system is the allyl system. So see here example, this is allyl system, CH2 double bond CH, CH2 minus. So this is Le anion. Le anion species. So it contains this negative charge is also involved in the process, involved in the reaction. So 3 carbons that we have to consider in the reaction. And this is odd carbon system. Another same CH2 CH CH2 plus, where allyl cation. Allyl cation is the species which we have to consider. CH2 double bond CH CH2 radical. So this is allyl radical. Allyl radical. So these are the species. We have to draw the molecular orbital for these species. Molecular orbital for these species. So molecular orbital, how can we draw molecular orbital? Now here 3 carbons are there. So 3 p orbitals are there. 3 atomic orbital and 3 molecular orbital here. So 3 molecular orbitals we have to consider. 3 molecular orbitals. Which are 3 molecular orbitals here? Psi1, Psi2 and Psi3. There are certain rules to draw this odd carbon system, molecular orbital of odd carbon system. So here 3 molecular orbitals. 3 molecular orbitals, Psi1, Psi2, Psi3. Okay. In even carbon system, we see that half are bonding, half orbitals, in total orbitals, half orbitals are bonding, remaining half anti-bonding. This is simple rule for drawing 2 pi electron system, 4 pi electron system or any other even system. So half bonding, half anti-bonding. This is simple rule. But here we can't make half of 3, half anti-bonding. Here in odd carbon system, one of the orbital is always non-bonding. One of the orbital is always non-bonding. So, and that must be always central. Always central orbital. So remember this thing. In odd carbon system, the one always non-bonding and that is always central. And remaining orbital, one is bonding, another is anti-bonding. So what is the rule? In odd carbon system, one orbital is always non-bonding orbital, which is having energy equal to unhybridized p orbital. So p orbital energy, and that is non-bonding orbital. In odd carbon system, one is always non-bonding orbital and which is always central. Remaining half are bonding and another half are anti-bonding orbitals, which are indicated by asterisk. So see how to draw these orbitals. Let's see here. 3 orbitals, Psi1, Psi2, Psi3. So this is non-bonding, NB indicated. This is anti-bonding, indicated by asterisk. See here, 0 orbitals, 1 orbital, 0 node, 1 node and 2 nodes. These are number of nodes. So the rules for drawing these nodes and antinodes. See here, rules for drawing these nodes and antinodes. So first rule is that draw the node for non-bonding orbital. Node for non-bonding orbital passes through carbon nucleus. For even Psi, for even molecular orbital, the rule is that one node passes through nucleus, carbon nucleus, and remaining in between the nucleus, remaining in between. So remaining in between. And third is for odd cyan. For odd cyan, all nodes pass between the carbon nucleus. Between carbon nucleus. So these are the simple rules for non-bonding orbital. All nodes passes through the nucleus. For even one passes through the nucleus and remaining passes in between the carbon nucleus. And for odd, all the nodal plane passes in between the carbon orbitals. So by using these rules, let's see here. 1, 3 atomic orbital, 3 molecular orbital. I am drawing all the 3's here. 3 atomic orbital, 3 molecular orbital. You see, first node here 0 nodes. So 0 node, that means we don't have to pass any node. Plus, plus, minus, minus, minus. We don't have to pass any node. Here one node is there. But that one node, it is non-bonding orbital. What is the rule for non-bonding orbital? For non-bonding, node passes through the carbon nucleus. So where node passes through the nucleus, through the orbital, so we don't have to draw the orbital here. So we are not drawing orbital here. So this is simple drawing node through the nucleus. For odd, this is odd number. 3 is odd number. So for odd, all the nodal plane pass between the nucleus. So this is between the nucleus, 1 and 2 nodes. So passes between the nucleus. Now give the signs. Plus, after node, sign becomes minus. Here minus, after node it becomes plus. Here plus, after node minus, after node plus. Here minus, plus, minus. So these are simple drawing of the orbital. Now here symmetry. See here it is M symmetry. When we pass the plane and fold M symmetry here, by passing plane we see that it is C2 symmetry, and here it is again M symmetry, because when we pass the plane and fold it, it gives the same coincide on the same sides. Same side coincide on same side. So M symmetry. Now see the electron distribution for these. Electron distribution for these. So electron distribution for these three, all these three species having the same molecular orbital drawing, but the electron distribution is different. See for anion, how many electrons are there? These are 2 electrons from this and 2 for this. So this is the electron distribution. What about cation? For cation, positive charge, that means it is deficient, but only 2 electrons are there. So electron distribution is like this. Electron distribution is like this. And for anion, for radical species, it is 2 electrons only, and radical species contain 1 electron. So this is electron distribution for the odd carbon system. Electron distribution, anion, cation, and radical. Let's see the cyclopentadienic system.